So, yeah, good evening. Let's get started with today's live interactive session on the Fluid and Particle Mechanics course offered on NPTEL. It is offered on NPTEL by Professor Sumesh Tampi and Professor Madhiwala Basaraj. I'm Shankar. I'm the teaching assistant for this course. I'm a PhD scholar from the Department of Chemical Engineering in IIT Madras. These classes are happening every week. From 6 p.m. to 8 p.m. on Mondays, but this week I was unable to make it on a Monday because I had some personal reasons, so I apologize for that. And yeah, let's get started with this week's questions. Any doubts you have, we can clear that out, and we'll do some practice problems as well. So let's get started with the questions that were there on the NPTEL website, on the SWAYAM website. And let us start with the first question, where liquid ammonia at minus 20 degrees Celsius flows through a pipe at 0.01 meter cube per second with a head loss of 12.95 meters. We just need to find the power required to start the flow. So for this, we don't have many information such as the density of ammonia. We just have the flow rate and the frictional head loss. So what we need to assume is the frictional head loss is basically the only loss that is happening, and for that we are pumping it with the help of with the help of any pump, and that pump has power associated with it, and you are calculating the power of the pump for this. So first we have to Google out what the density of let me keep it as not NS3 but ammonia is, and at minus 20 degrees Celsius everything has I've seen many reports and questions that have varied this value of ammonia. So let us take the ammonia, which I commonly found to be 665 kilograms per meter cube. And the flow rate of ammonia through the pump is 0.01 meter cube per second. The head loss is 12.95, and this is in meters, and the gravity is 9.81 meter per second square. So the power required just happens to be a product of all the terms that has been given. Rho Q G HL. How this comes is basically as follows. So rho times Q will be the mass flow rate, and that times G will give you the weight, the flow of flow in weight, or let me call that as mass times G upon time. And if we multiply that with H, we'll get the rate of change of energy per unit time, which is basically the power. So the density of ammonia happens to be 665 kilogram per meter cube times 0.01 meter cube per second times 9.81 meter per second square times the head loss, which is 12.95 meters. Therefore, the power associated with this required to drive the flow comes out, after calculation I got around 844 watts. which does not match the answer that has been given in the SWAYAM website, but I'm curious to know if anyone else has a different solution. So if you do have another solution, please feel free to let me know in the comment section of this. So I'll just wait a second for you to catch up, and then we'll move on to the next question. Okay, I hope there are no doubts here. We'll move on to the next question, where it is said that benzene at 20 degrees Celsius is to be transported through a 0.5 meter long, smooth, 20 centimeter diameter horizontal pipe. It is desirable to obtain maximum flow rate but maintaining laminar flow conditions without moving to transient or turbulent flow conditions. The maximum pressure drop for which laminar flow can be obtained is dash Pascal. So what we have to do is just find the pressure drop that is associated with this laminar flow, and we have to start by equating the Reynolds number to the highest value of the laminar flow, and it is given that it is the flow is through a smooth horizontal pipe. So we know that for a pipe, uh, the Reynolds number given by rho d by mu should be less than or equal to 2100 to be in the laminar flow regime. If it's a value greater than 2100, it goes to transition flow regime, and if it's greater than 4000 or 3000, it goes to turbulent flow. So let us consider the maximum value of 2100, and we know that benzene, if you Google it out, I mean, I think this part of the uh, this part of some research is required to answer this question. Research in the sense that the density of benzene is not given directly. We just have to Google it out, and when I did that, I was able to find the density of benzene to be 876 kilograms per meter cube. Similarly, I found the viscosity of benzene to be equal to 0.65 centipoise, which is 0.00065 poise. Now, we know the density, we know the viscosity, we know the diameter of the tube, we can find out the velocity, assuming that it is in the laminar flow conditions and maximum flow rate has been obtained. So, and the diameter of the pipe is 20 centimeter, which is 0.2 meter, and the viscosity of benzene is 0.00065. Okay, sorry, this is not in poise, this is actually in its SI units of kilogram per meter second. So the velocity can be found out from here. So I'll give a minute for you to complete out the calculations, and let me just complete the method how to proceed after you have found out the velocity. Just put it in the some equation you're all familiar with, which is the Hagen-Poiseuille equation for laminar flow, and we can get the pressure drop delta P as 32 times mu V L by d square. I think we have all the values that is required to solve this. All we have to do is substitute the value of V, and in this equation, this equation, we have mu, we have the length and the diameter of the pipe that is given here, and that's all we have to do. So I'll give a couple of minutes for you to find out the answer here. Meanwhile, let me substitute for the pressure. So just let me know if you have an answer. The velocity is somewhere around 0.0078 meter per second. So if I substitute that 0.0078 meters per second, I'll get the delta P to be equal to 0.00203 Pascal. Yeah, so this is what I get after solving for the second question. Please let me know if you have found this, if you have gotten the same answer, or if there is any difference in the answers. Let's move on to question number 3, where it is given that water is flowing in a pipe at 1 meter cube per hour between points A and B. Mercury manometer connected between these 2 points gives a reading of 35 millimeters, and pipe 1 is 1 centimeter in diameter, and the pipe is 1 centimeter in diameter, while the length of the pipe between points is 50 meters. However, the pipe is not horizontal, but rather the point B is 30 centimeters below point A. It is given that the pressure at A is higher than that B. Assume room temperature. So first question is the direction of flow is from A or B, or is it cannot be determined or not enough to predict. First, let's try to draw out what the flow looks like. First, we have a pipe that in which A is elevated and B is 30 centimeters below A. So this is what it looks like, and it is given that a mercury manometer that is connected here, although it looks not very neat, it does the trick of a YouTube manometer. So let this be point A, let this be point B, and it is given that pressure at A is higher than pressure at B. Therefore, therefore this part here, the limb in A would be lower than the limb that is there for B. And let us assume that this is filled with mercury, because we have it's been told a mercury manometer is used, and the difference between these two lengths is of gives a reading of 35 millimeters. So the mercury manometer limb is 35 millimeters. Now it is also given that the distance, I'll go back to black ink, the distance from A to B is 50 meters, and the point B is in fact is in fact 30 centimeters below B. The point B is 30 centimeters below A. And from looking at the figure itself, it is quite obvious that it is given that PA is greater than PB, and HA is greater than HB, which means flow in both these conditions, flow that has to be generated with both these conditions has to be from A to B. So the correct answer is A, option A. Okay, let's move on to question number 4. We have to find the same part of the introduction is given here, where water is flowing between these two pipes. You have to find the average velocity here. Yeah, and we can find the average velocity by considering the volumetric flow rate and dividing it by the area, which is pi d square by 4. And the volumetric flow rate Q is, sorry, that's not zero, it's like 1 meter cube per hour, which is 1 by 3600 meter cube per second. And the diameter is 0. Yeah, 0.01 meter, which is given around here as 1 centimeter, which is 0.01 meter. Therefore, if we do this calculation, we get V to be 1 by 3600 meter cube per second divided by pi into 0.01 square by 4 in meter square. And we'll get this to be approximately equal to 3.53 meters per second. So I'll give you a minute to solve it out for yourself. Let me know if you have any doubts. It's a very basic concept. Just divide the volumetric flow rate with the area and you will get velocity. Okay, let's move on to question number 5, where it is said that, where it was asked that the manometer reading will be option A proportional to head loss, option B inversely proportional to head loss, option C will be a constant, option D will be proportional to the square of the head loss, and option E will be inversely proportional to the square of the head loss. So the manometer limb reading will be basically rho times the manometric fluid, which is mercury, times D times H in the limb, and that is proportional, and that is actually proportional to the head loss, the proportional to the head loss. So the correct answer is option A. The manometer reading will be proportional to the head loss. Okay, let's move on to question number 5, where we have to find the Reynolds number. And Reynolds number is rho v d by mu. Here, not R, but the density is water, which is 10 raised to 3 kilograms per meter cube. The viscosity is 10 raised to minus 3 in kilogram per meter second, and the diameter is 0.01. Sorry, it's not centimeter, it's in meters. And the velocity we just found out in a couple of questions previously is 3.53 meters per second. Therefore, the Reynolds number is, just substitute the values for Reynolds number. And when you do, you will get the value that is close to 35,367, which indicates that this is in a strongly turbulent regime. As this Reynolds number is given for a pipe flow, this is very, very turbulent. Okay. Uh, Now the next question is a little bit interesting because it's stated that if the flow is assumed to be laminar, imagine that you are in a world of zero disturbance and you have atomically smooth pipe. That flow can remain laminar for any Reynolds number. Then the friction factor can be calculated as. So for this, we know that for laminar condition, the friction factor F is in fact given by the fanning friction factor, that is given by 64 by Reynolds number. So this should be 64 by 35,367, and which would come around to 0.0018. Yeah, and this is the friction factor that is calculated as per laminar flow conditions, even though the Reynolds number is sufficiently high. So let's move on to the next question, question number 7, where we have to calculate the pressure drop across A and B. And here what is given is that the pressure drop gives a reading of, excuse me, yeah, there is a pressure drop reading of 35 millimeter, which can be used to calculate the the pressure across these 2 points, and that is in the manometric fluid limb, that is 13,600 times 9.81 times okay, this pressure drop is calculated as rho gh, but a small difference is that it is the mercury that is being calculated, rho times g times the manometric fluid reading h. I'm not marking it as L, I'm just keeping it as h. And the manometric fluid reading is 35 millimeter, which is 0.035 millimeter. Therefore, the pressure drop comes out to be equal to somewhere between 4,669 Pascal. And question number 8 asks us to find this head loss in meters. So the head loss is basically the given by the pressure drop, and yeah, for that we have to use the density of water here, and here it would be the head loss that is being taken into account. So head loss will be delta P by the flow, the fluid inflow times G, density of the fluid inflow times G, and this should be 4,669 Pascal by 1000 kilograms, excuse me, per meter cube times 9.81 meter meter per second square, and yeah, this value would come out to be 0.476 meters. Let me know if you have any questions in these 2-3 problems that we have done together. I'll give you a minute to catch up. Okay, now that I've given you a minute, I hope we can move on. Where we just have to one part left of this multi-part question is to calculate the friction factor, and for that we need to take a look at the formula for the head loss, which is given by HF or HL, and it's given by F times L by D times V square by 2G. And it is 4F if we are talking about defining friction factor. So we just have to substitute these values over here. It would be 0.476 should be equal to 4F times 50 by 0.01 times 3.53 squared by 2 into 9.81. And you can calculate this, and I'll give you the answer in a minute, but let's see if you're able to do this on your own. And the answer would be 0.0003725. See, this is quite different from the Fanning's friction factor that we obtained in equation or question number 6, where we got 0.0018. Okay, we'll move on to the next match the following question, where we are supposed to match each of this with the figures that are shown. So first we have to find out what the growing brown boundary layer is, and that is actually, you can see that as we progressively moved from here to here, or if we move in this direction, what we are seeing is a boundary layer that is given by this dotted line that keeps on increasing, and that is option A. So the correct answer to this part is option A, which is the growing boundary layer. Okay, second part is the inviscid core flow, and this central part is supposed to capture the inviscid core flow, where we get turbulent excuse me, near turbulent conditions, and it's in this part. Third one is boundary layer merge. As you can see, the dotted lines have represented the boundary layers, and they meet at the point C. Therefore, the option 3 has the correct answer to be C. And after this particular point, where it is shown at this particular point, we see that the flow field is in fact fully developed, and it is developed velocity profile. It shows the characteristic of a developed velocity profile, and the entrance length that is required by the fluid to become fully developed flow is given by the entrance length, the letter E, and all the points after E that constitute F would be characteristic of a fully developed flow regime or the region. Please let me know if you have any doubts. These are pretty straightforward from what was discussed in class. So, yeah, there you go. Okay, let's move on to the final question in the graded assignments. I believe I have not added the options here. Just hold on a second. It's yeah, sorry about that. I have not copied the question completely onto my iPad. So let me just write down what they are. Option A, B, C, D, E, F, and linear, viscous, sublayer, logarithmic overlap. Overlap layer. U plus is equal to U by U star. Y plus is equal to Y U star by V. Sorry, Y star BV. And inner layer. Yeah, so I feel that I have not written down this path, so we just do this quickly now. So they was just to identify which part of the graph each of them belong to. Let's start by identifying the axis. We know that this is a plot of the non-dimensionalized velocity on the y-axis versus the non-dimensionalized distance on the x-axis. So let's mark that right now as D is U plus, and the option B is I'll just write down the answers instead here on the left side. So this is D, this would be B. Y plus is on the x-axis, which is given by the letter B. Yeah. Now, what is next? Let's start from the bottom, which is option C, where you can see that it is actually the inner layer that is being portrayed as per the discussions that is given in the class. And option option F would be the linear viscous sublayer, which corresponds to a U plus equal to Y plus, and at the location E, it would be a logarithmic overlap that's happening over here, and from here to here we have the overlap layer. So E goes to logarithmic overlap and A goes to overlap layer. Okay, let's finish off the practice problems. And this question is very similar to the one we had discussed earlier. The water is flowing at a pipe of 2.71 meter cube per minute between points A and B, and the mercury meter gives a reading of 135 millimeter. The length of the pipe between points A and B is 5 meters and 5 meters long and 6 meters centimeters in diameter. However, the pipe is not horizontal, but the the point B is 3 meter above point A. It is given that the pressure at point A is higher than at point B. Therefore, we just need to figure out whether the pressure at point A, from a pressure difference between point A to B, can handle a head loss of uh, head loss of 3 meters. So first we find out the pressure that is associated with this manometer fluid. Delta P is equal to rho HG H, which is 13,600 times 9.81 times 0.135. Yeah, you'll get this as 18,000 or 18 kilopascal. And if we have to find out the head loss, it has to be this delta B divided by, since it's water, we just have to use the value of water here. And it will be 1.836 meters. Therefore, the flow will be from A to B. Okay, now it is also giving that the flow is assumed to be laminar. Again, as per the similar assumptions we have done here or done previously, we have to find out the friction factor. And for that, we first need the velocity, which is obtained from the volumetric flow rate times pi d square by 4. And the volumetric flow rate is given out to be 2.71 meter cube per minute, which is 2.71 by 60 meter cube per second, and the diameter is 6 centimeter, which is 0.06 meter. Therefore, the velocity is 2.71 by 60 times pi times 0.06 square by 4, which comes out to be 15.97 meters per second. Therefore, the Reynolds number in this problem would be the same as what you can calculated as rho Vd by mu, which is 10 raised to 3 times 15.97 times 0.06 by 10 raised to minus 3. and this value will come to 0.4. Oh, yeah. 95820. And the friction factor is given by 16 by, sorry, this is 64, excuse me, 64 by the Reynolds number, which is 64 divided by 95820, which will come out to 0.00067 as the answer. Option F here would be the right answer. Okay, moving on to question number 3. What would be the head loss? We just have found out the pressure drop. We just have to divide it with the density of the fluid in flow, that is water. And we found that the pressure drop was, in fact, we have even found the head loss to be equal to 1.836 meters. Yeah, moving on to question number, this is actually question number 4. The power required to drive this flow, which contains water at 20 degrees Celsius through a pipette to a 0.02 meter cubes per second with a frictional head loss of 12.95 meter. And as we saw earlier, power is rho times Q times G times the head loss, which is 10 raised to 3 times 0.02 times 9.81 times 12.95, and this power would be equal to 2540 watts, but the answer has been asked in kilowatts, so it's 2.54 kilowatts. Let's complete the last question that's associated with the non-graded assignments, where glycerine, whose viscosity and specific gravity are given, flows through a 1 meter smooth 10 centimeter diameter horizontal pipe. The maximum pressure drop for which laminar flow is expected is, again, we know that the maximum allowed Reynolds number for laminar flow is 2100, and we equate that to the glycerine's glycerins for density and viscosity. So it's given that the glycerin has a specific gravity of 1.2, therefore glycerin's density is 1.2 times 1000, which is 1200, and the viscosity of glycerin is 1.4 kilogram per meter seconds. Therefore, oh, this is, excuse me for writing it wrongly, it's not G, it is V. And here we are having to find V, therefore it is 2100 times 1.4 divided by 1200 times 0.1. which will be 24.5 meters per second. Can confirm this calculation afterwards. And we just need to substitute this in the Hagen-Poiseuille equation given by delta P is equal to 32 times mu VL by d square. And this is 32 times 24.5 times 1.4 times the length is 1 meter and the diameter is 0.1 meters. And the pressure you would get here would be 109.76 in kilopascal as per that has been asked. Okay, I guess that is it for today. We still have a couple of questions from week 7 that we need to do. Maybe I'll try to finish it off in one of the summary classes that I have to do. Sincerely, thank you for your time and attention. Please feel free to contact me if you have any doubts. Thank you.